Okay, so we covered the hard part, which is distance versus time. It's a little bit more, unexpected. So now let's cover the easy part. So this is speed versus time graphs. So again, the important thing to remember with these graphs is the word that it gives you. One will say speed, one will say distance. That's how you know how you should read it, right? So it's like a language that's very similar, but it's slightly different. So with that being said, let's look at this graph. So this is a speed-time graph, speed versus time. Below represents the motion of a car, match the description. So we're just matching the description. It's pretty easy, pretty straightforward. This is the stuff that you've probably used to growing up. So let's look at E. Again, Y is speed. So as you increase on Y, your speed increases. X is time, right? So with E, the object is slowly increasing its speed steadily. So that means it is slowly accelerating, right? Over time. So it's obviously not stopped. It's not at a constant speed because remember, if there's a slope, the speed is changing. So this means it's accelerating. So this is actually 7, right? So it's accelerating. So 7 is E. So bam. And because here you're just going to write that it's a positive constant acceleration. Right? Okay, so let's look at number 6. Or actually, let's just go E, F, G, H, right? So let's look at F. So this is sort of the opposite of E, right? So it starts off, it looks like it starts off very fast because it's up at the top of this Y slope. And over time, it goes down, right? So this is accelerating also. I know that sounds confusing, right? But now you're in physics, so get used to the term accelerating. All that means is a change in speed. So just to reiterate, this is accelerating, this is accelerating. Positive acceleration, negative acceleration, right? Change in speed, right? So I realize this is vague, but this is also like the second or whatever unit. It's pretty early in the physics year, so they'll get more specific. So just keep that in mind. Acceleration means change in speed. So this is negatively accelerating over time, i.e. it's slowing down, right? So that looks like 8, right? It's slowing down. So graph F matches 8 because, well, it's slowing down, right? You can say slowing down. If you want to be a real baller, put it's negatively accelerating. Cool. All right, let's look at G. So we have our speed. Remember Y. This is the Y. This is the X. The speed is constant, right? It's not changing over a period of time, which means it's like on cruise control or something, right? Whether that's 5 miles an hour or 100, whatever, it's constant, right? So the car is traveling at a constant speed. So G looks like it has to be 6, right? And you can say because it has no slope that is greater than 0, that's a little confusing. You can just say it's a constant, right? It's a horizontal line, right? Horizontal line above 0. So let's look at H. H, there's only one left and you pretty much know it, but since 0 speed is all the way at the bottom and it doesn't change, it means it's not moving, right? So it's pretty straightforward. So the car is stopped. Why? Because the speed is 0 for the entirety, right? Okay, so let's move on to the next page. Guys, remember, if you feel like this stuff is easy and you can move way faster than me, then turn the video off and do it, and maybe watch the video to check it if you want. So you don't have to do this. This is just, it's going to take a little longer than what you would normally do, but that's, the trade-off for getting the answers, I guess, right? All right, so let's look at this. So before we even read directions, let's look at the graph. I see its distance versus time, right? So that's important to know. It's distance versus time graph. So that means that we need to read it as a distance versus time graph, right? So let me make sure my phone doesn't go off in the middle of this, because it probably will. That's okay. All right, so we're reading it as a distance versus time graph, so let's keep that in mind. So look at the graph above, distance versus time. It shows how 3 runners ran a 100-meter race. I'm just going to underline this, not a big deal, but I'm going to do it. Actually, I'm going to box it. All right, which runner won the race? Okay, so remember, this is distance, right? Once they get to the top, it's a 100-meter race. That means it's the end. So they all finished, right? They all made it 100 meters. But let's think about this. And this is not deep, but I just want to explain it anyways. Whoever finished the race in the least amount of time obviously did it the fastest, right? So they're the ones that won the race, right? So if you just look at this and you don't think and you're like, oh, that's the furthest line. Well, that's not right because this person finished it in 16, 17 seconds, right? Whereas Albert finished it in 12, right? So Albert won the race, right? So keep that in mind. Like, we got to learn how to analyze and read this graph. Albert won the race because he finished the 100 meters in the least amount of time, right? So which runner won the race? Albert, because he ran it in the least amount of time, right? That makes sense. Okay, so which runner stopped for a rest? Obviously, this is a quick one-word answer. This is important in every single answer. Don't give me halfway answers. If it says explain, explain. It doesn't mean write 100 paragraphs. It just means like, yo, give me like a sentence so I know you're not just randomly guessing, right? So, which runner stopped for rest? Obviously, the only difference in these three runners is this one, Charlie. So obviously, Charlie's the answer, but I don't care about the name. I care about the why. Because if you know the why, you understand it. If you don't know the why, then you don't know anything, right? You're just a really good guesser. So, remember, distance versus time. So if we look at Charlie, remember, distance is if it moved up or down. This is the distance. If his distance did not move over a period of time, then he was stopped, right? So if I say, hey, how long is it going to... I'm timing you to seeing how far you can run in 10 seconds, and I start my stopwatch. In 10 seconds, you move 0 meters. I don't have to be a genius to know that you did not move at all. If your distance was 0 in 10 seconds, you did not move. So in 8 to 10, that's 2 seconds. To 12, that's another 2 seconds. So at 4, we're at about 5 seconds, his distance didn't change. That means he was stopped. So that's why it's Charlie. There's a flat horizontal part on his line, or if you want to be a little more detailed, that his distance didn't change for a period of time. All right? How long was the stop? That's easy. Remember, this doesn't mean it's 8 seconds. It just means at the 8-second mark, he stopped for 9, 10, 11, 12. So we're at 4, right? 13. We'll call that about to 13. So from 8 to 13 seconds, what is that? 2, 4, 5. He stopped for 5 seconds. Okay? So again, it wasn't 8 seconds. It wasn't 13. It's these from here to here. That's 5. How long was the stop? We just did that one. How long did it take Bob to complete the race? Okay. Well, he started at 0 seconds. He ended at 14 seconds. So it should be 14 seconds. That's when his line reached 100 meters. So that's easy. Calculate Albert's average speed. So, you're going to need your formula chart. Hopefully you have one. If you don't, come and ask me, and I'll get it and keep it. So our formula for average speed is average velocity equals distance divided by time, right? Average distance, average time. So, who are we talking about? We're talking about Albert. Albert's distance was the same as everyone else's distance. 100. Right? They all ran 100. Albert, Bob, Charlie, all 100. So that's easy. Time. Albert's time was 12 seconds. Right? 12 seconds. So we got 100 divided by 12 equals 8.3. In the calculator, it should be repeating. We're just going to say 8.3, put that. And then almost as important as your answer is your units. Meters per second. Units are extremely important. If you put the wrong unit, your entire answer is wrong. Make the habit now, because 5, 10 units later, it's going to screw you over, or it's going to make things easy because you'll automatically know. Right? So, meters per second. I automatically know when I see this. If I didn't see anything on this paper, but I saw meters per second, 100% I can tell you that's a velocity. Because velocity, the unit is meters per second. Or it's distance per time, right? So keep that in mind. Anyways, our answer is 8.3 meters per second. Easy. Easy money. Alright. Okay, so let's go to this one. Alright, so take a look at the graph. Give it a second. The graph below shows how the speed of a bus changed during part of the journey. Okay, so we're saying the speed changed. So what kind of graph is this? immediately I'm going to look, highlight, do whatever. Speed versus time. That's important. Okay, so choose the correct words from the following list to describe the motion during each segment of the journey to fill in the blanks. In other words, from letter to letter, you're describing it. That's it. So the first one they're saying, yo, from 0 to A, O to A, whatever. So from here to here, the bus is blank. Its speed changes from 0 to 5 in 5 seconds. So our answer choices are here. Accelerating, decelerating, constant speed, or rest. 100% from O to A, we can eliminate at rest because it would be a flat line. And we can eliminate constant speed because it would be a flat line, right? At rest, it would be a flat line at 0 speed, because this is the y is speed, right? And at constant speed, it would be a flat line anywhere above 0 speed. So because it is a positive slope, its speed is increasing over this period of time, it's going to be accelerating. Okay, so accelerating. I don't care if you misspell that. Okay, so segment A to B, that is here to here. We just said if it's a flat line, it's either going to be a constant speed or at rest. So we already are down, we've cut 2 of our answer choices away. Easy, right? Because it's at the 10 meters per second up here, that means constant speed. So that's easy, constant speed. All right, so we've used a couple of them. Notice that there is 1, 2, 3, 4, 5. So don't automatically assume you're going to use each one once. That means one's going to be used more than once. Maybe multiple will be used more than once. So just keep that in mind, right? So B to C, that's here to here. Automatically I see that it's not constant speed, and I see that it's not at rest, and I see that the speed decreased over time. Actually pretty rapidly, like it smashed into a wall, you know, honestly. Like it goes from 10 meters per second in 10 seconds at second number 10 to, so 3 seconds later it stopped. So it probably just slowed down pretty rapidly. It didn't smash into a wall, but nevertheless, it slowed down, right? So that would be decelerating. D-E, C-E-L, rating. Cool. C to D, flat line. It's one of these two. 0 meters per second equals at rest. Or smashed against a wall. Okay, D to E. Well, that tells me it didn't smash a wall because now it's starting to speed up again. So that is not flat, and it is a positive slope. So that means it was accelerating. It's probably habit to put 2 L's, but there's actually 1 L. I always want to put 2 L's. Only 1 L though. Okay, so that page is done. Awesome. Let's move to the next page. Notice with these units, they start you off and they give you a ton of explanation, and then they start giving you less and less, and it's more for you to figure out, right? What you guys got. Okay, so consider the position versus time. Whoa, what is that? It's not speed and it's not distance. Well, position is distance, right? So don't be confused. Position and distance, same thing for our purposes. So you got 2 cyclists, 2 bicycle riders, right? Do the cyclists start at the same point? Remember, distance, time. Let's assume it's 0 to 10 meters, whatever. This is the 5 meter mark. So this person starts at 0 meters, and this person starts at, we'll say, 4, right? They didn't start at the same point. So no. Why? Because their initial points are different on the distance side, the y-axis. If not, which is ahead? Well, if you're racing somebody, and let's say you are extremely faster, you're so much faster than them, right? But you know if you started the same, the guy's going to be like, no, I'm not going to race you because you'll kill me. So you might be like, okay, bro, check it out. You start at the 5-yard line, and I'll start at the 0. That way it gives a little better chance. So this person started a little bit ahead, right? B started a little bit ahead. So which one is ahead at the very beginning? It's B. obviously, and I'm looking at the slopes here without even going to these next questions. I can see, well, they probably started ahead because look how slow this person is. Jeez, oh man, they barely have it's almost a flat line. It's like a turtle. Versus A, it's pretty slanted, right? Okay, let's look at B. At time equals 7 seconds, which cyclist is ahead? Okay, so if this is 5 seconds, I'll just randomly say this is 7, right? And we dot this up. Ahead means furthest on the distance. So A is about there. I know this is not really super accurate. B is about here. Looks like A is ahead. At 7 seconds, A is ahead because their line's further up. I mean, there's no other way to put it. They have a steeper line, right? C, which cyclist is traveling faster at second 3? Okay, 3 we'll say is about here. Boom, 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 boom. So don't be confused by this, because this is like I'm going to see if I can trick you guys question was what they're doing. Because when you see this, you're saying, well, okay, well, if we do the same thing we just did, well, B's further ahead. Is it asking which one's further ahead? No. It's asking which one is traveling faster. If we're racing and I'm further ahead, we're racing a marathon and I'm a mile ahead of you and I'm running 5 miles an hour and you're running 15 miles an hour sprint, I'm ahead of you, absolutely. I'm a mile ahead. But you are going faster, right? So which one's traveling faster? The one with the highest slope. That would be A. So don't be thrown off by that, right? A has a steeper slope, he's going faster. D, are there velocities equal at any time? Okay, so velocity, think of this as interchangeable, even though it's not exactly the same thing. Velocity and speed, same thing, right? So, are there velocities equal at any time? Okay, this is curveball question number 2. Velocity and speed here is the slope, the sharpness, up, down, not very much up, whatever. So, are they equal at any time? The fast twitch thing that people always say real quick and they get it wrong is like, oh yeah, 5 seconds. See, they're intersected right there. Does that mean they are traveling the same speed or velocity? No, not even. That means that they're at the same distance. If me and you are racing and I'm 20 times faster than you, I let you have a huge head start. At a certain point in time when I go to pass you, if we freeze, we're going to be at the same distance, right? I'm going to be neck and neck with you at that frozen moment. But as soon as we unpause, I'm going to blow past you. So all this intersection means is they were at the same distance as A blew past B, right? So are their velocities equal? No, they're not. They have the same, because the steepness is different, so they are never equal. And we kind of answered E already. What is happening at the intersection of A and B? Intersection just means the crossing. That just means they're at the same distance point. So at the same point at the same time. You could also say, hey, A is passing B, but the best answer is, yo, they're at the same point at the same time. All right, let's keep going. Okay, so you got 2 graphs. We're still talking about cyclists. Consider the new position versus time graph for A and B. New graph, previous graph. So old, what we just looked at, new. How does the motion of cyclist A, so I'm going to start highlighting new, right? So how does the motion of this guy, A, in the new graph compare to the motion of A in the old graph? So you're comparing A's from new and old. Well, from what I'm looking at, they're about the exact same. They look the same. Same slope. All right, B. How does the motion of cyclist B in the new graph, new, compare to the motion in cyclist B from the previous graph, old, right? Well, it looks like in the new graph, because it is distance versus time, it looks like they're running backwards because their distance has decreased, right? It's going the opposite direction. Remember, don't be confused. It is distance versus time. If it's sloped like this, they're running away from something. If it's sloped like this, they're running towards it, right? Okay. So whatever you're going to put, going backwards. C, which cyclist has the greater speed? Okay, they're not asking which direction, which one has the greatest speed. Well, look at the steepness of the slope. A is still steeper, so A has the greatest speed. Describe what's happening at the intersection of A and B. The same thing was happening last time. They're at the same position, right? They're at the same point in distance-wise, right? Same position. I have bad handwriting, but that's okay. You can hear me. Turn on closed caption. All right, E. Which cyclist traveled a greater distance during the first 5 seconds? Well, that's going to be, again, the highest change from here to here, right? Because, let's see. So, when you look at A, because he had a steeper slope, that means he covered more area because he traveled at a faster rate, and he also covered more area from 5 seconds. So, B only went from here to here. A went from here to here, right? So A. Steeper slope. However you want to explain it. Alright, let's keep rolling. Jeez, oh man, this is never ending. Okay, a few more pages. We're almost there. It's okay, it'll all pay off. Alright, displacement of velocity. So, this is our middle position. Position versus time. It's dealing with a minivan. A minivan travels along a straight road. Initially starts moving towards the east at a constant speed. Below is the position versus time. So, remember, it's position versus time. Okay. Does the minivan move to the east? If so, during which time interval? Remember, it is distance versus time. From here to here, the distance did not change. Did they move if the distance didn't change? No. So it didn't even start moving. 0 to 10 seconds, it didn't move. Then it started traveling east, like they said up here. Hopefully you guys read that, right? Or just listened when I read it. So, does it move to the east? Yes. Which time interval? Well, 10 to 20. Actually, no. 10 to 40. Because here, it's moving back to the west, because this means opposite direction in a distance versus time. And then 60 to 70, right? Keep this in mind, because there's a few pages later you have to do something like this. And if you don't know this, it's super confusing. All right, number 2, does the minivan move to the west? Yeah, absolutely. From here to here. So 40 to 50. All right. Is the minivan speed between T1, this point, and T2 greater than or equal to or less than T2 and T3? So from here to here is faster because the slope is like stronger than here to here, right? So it's greater than. Greater than. Is the minivan speed between 4 and 5? So 4 and 5 is here to here. That is very fast speed. It's a different direction, but it's very fast. Greater than, less than, and equal to 6 and 7. That's not really a fast speed, so it's greater than. It's actually much greater than because it's so steep of a slope. They're going the opposite direction, these two, but this is definitely going much faster. Do they ever completely stop? Yeah, actually they do. 2 times, right? So 0 to 10 seconds, like we talked about earlier, because the distance doesn't change, and 50 to 60. So 10 seconds here, 10 seconds here. Does the Miniman ever move with a constant velocity? Yes. So, again, remember, this is a distance versus time. So every slope you see, every smooth line slope is a constant velocity. It's not an acceleration. Hopefully I didn't make a mistake and say that at all during this. Maybe I did, but so from 10 to 20, that's constant. And then from 20 to 40, that's a constant. It's not 20 to 40 meters per second. No, it's second 20 to second 40. In other words, for 20 seconds, for 10 seconds here. And then from 60 to 70. I guess I should put T6 to T7, T2 to T4. That'd probably be less confusing. What is the total displacement? Okay. What does displacement mean? Hopefully you remember this from the vocab. Displacement means how far are you from the starting point. It does not mean how far you've traveled. If I'm running a mile, right, this is my track. I start here and I run all the way around to the starting point. My distance is 1 lap, we'll say. My displacement, that's distance, my displacement is 0 because I am not far at all from where I started in the same spot. So if they started at position 5, doesn't matter what they did in between, they ended at position 0. So the difference between position 5 and position 0 is 5 meters. Their displacement is 5. Hopefully that makes sense. Ask me if it doesn't. Alright, so motion. Is this the last one? Because I am tired of doing this. I know if I am, you guys sure are too. Alright, 3 more pages. Hang in there. We can do it. Whew. That's why I record it, so I don't have to do it 100 billion times. Okay, so motion. Here we go. What does the slope of a distance versus time graph indicate about the object, excuse me, an object's motion? So when we're talking distance versus time, it indicates its velocity. In other words, how fast. What does the slope of a speed versus time indicate? Okay. You want to say speed, but don't put speed. It's actually acceleration with 1 L. Because it has 1 L in it, even though it looks like it would have 2. Okay. Let's do the next one. Side note, some of these can have multiple answers. Okay, which shape fits a distance versus time graph of an object moving at a non-zero speed, distance versus time? So it's moving at a non-zero speed in its distance versus time, but it's also constant. Keep that in mind. So, distance versus time, not moving, not moving. Accelerating, decelerating. Constant speed in a distance versus time is C. Because its distance is constantly changing. Smooth. Okay, next. Before I even read, speed versus time, constant, non-zero. Speed versus time, constant, non-zero. That's 0. That's remember, speed versus time, we just said it shows acceleration. Acceleration, acceleration, deceleration. Speed versus time equals B. Constant speed. Alright. Distance versus time. Which 2 shapes? We're going to have 2 answers. I'm just going to put my comma right now. Motionless. So it's not moving. It is distance versus time. Distance is not changing. So A. Distance is not changing. B. You dig it? Alright. Which shape? Speed versus time. Motionless. That's got to be A. It's going 0 for it's motionless, meaning it has no speed. Good. Number 7. Which shape fits a distance versus time graph of an object? So distance versus time, and it is speeding up at a steady rate. So that looks like C. Distance is smoothly changing over time. Steadily, right? Actually, no. Sorry, not C. I screwed up. D. So that means it's accelerating. You know what I'm saying. Cool. So that's D, not C. Sorry about that. Hopefully I didn't lead you off a cliff. That was a test. I wanted to see if you knew. Yes, that's what it was. All right, 8. Which shape fits a speed versus time graph of an object that is speeding up? So speed versus time, speeding up. So this should be an easy one because that's not it. That looks good, speeding up. That's accelerating and speeding up. That's decelerating, right? So this is definitely C. Cool. Okay, which of the following units? Okay, this is what I was talking about. If you know the units, you know what it's talking about. So this is the next 3 questions. They give you units, and they want you to tell you like the equivalent, right? So let's look at the first one. What is equivalent to meters per second per second? Well, S times S is what? So meters per second squared. Meters per second squared is this. Side note, that's always talking about an acceleration. All right, number 10. Which corresponds to distance versus time? What do we say about distance versus time? It's a velocity. Velocity is always meters per second. Bam. C. Too many C's. Meltdown. 11. Which of the following corresponds to the slope of speed versus time? Speed versus time is an acceleration. Ah, meters per second squared. That is an acceleration. So that would be C again. Do you see? Lol. Alright, let's go to the next page. Whew. Hang in there. Doing good. Almost done. Got a lot. This is day 3. Jeez, oh man, if you're here and it's only day 1, you must be doing good. Can you even see that on your end? Let's refocus. Here we go. We'll take it. I'll read it. So the table below gives the distance and time for a moving object. So they give you distance points, they give you time points, and they want you to figure it out. So which of the following distance versus time graphs corresponds to the table? So let's look at this. At 0 seconds, it's at 0. So what does that mean? That means it can't be B because it's 0 seconds. This is up here. So we got to eliminate that. At 10 seconds, it's at 100. So it can't be D because at 10 seconds, D is gone. So we're looking at A and C. So let's look at some of the middle ones. It doesn't move until 4.5 seconds. It takes a little bit of time. And then it moves 20, 40, 60, pretty evenly, but pretty quickly. So it doesn't move hardly at all. Well, excuse me, let me rephrase that. It moves very slowly from 0 to, because it takes 4.5 seconds to get to 20. And then all of a sudden 20 more takes only, what is that, less than 2 seconds? And then 20 more takes what? A little less than that. And then 20 more takes like a little more than a second. And then 20 more takes 1.1 seconds. So that looks like it is accelerating very rapidly, not smoothly. So I would go with C. Okay, which of the following descriptions matches the graph you selected in number 12? So, matches this graph. So, a motionless object? No. An object moving at constant speed? No. An object undergoing constant positive acceleration? Well, that's positive. And there is no negative because nothing's sloping down, right? So that would be C. Looks like C, yeah. All right. Which of the following speed versus time graph corresponds to the table? So now we're saying, yo, speed versus time. So it's pretty smoothly accelerating over the period of time. So it's definitely not motionless. It's definitely not slowing down. It's definitely not moving at a constant speed, because these times would be even. It would be like 2, 4, 6, 8, 10 if it was constant. So I would go with C, constant deal. Oh, we didn't put 14, right? All right, so. Okay, here we go. Number 16, woman walks away from her starting point in a straight line. It just shows her motion, blah, 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 blah. Describe the woman's motion between 0 and 2 seconds. It looks like she is, because this is distance versus time, she covers more ground faster and faster, so it looks like she's accelerating. So it looks like she's speeding up. Alright, B, fill in the table below. Rate her speed. So keep in mind, speed is distance divided by time. So you're going to have to calculate these. So from 2 to 4, she covers, so she's at the 2 meter mark and she ends at the 8 meter mark. So she goes 6 meters. So her distance is 6. Her time from 2 to 4, 2 seconds to 4 seconds is just 2. That means her speed is 3. From 4 to 6, she's at 8 meters and she's still at 8 meters. So her distance is 0. Her time is, does it really matter because you're dividing into 0, right? So that's 0. 6 to 8. Her distance is 8. So her distance goes 2 meters. Her time is 2 meters. 2 divided by 2 is, oh, I was not even showing you guys that. There we go. Come on. Easy. Cool. Almost done. Ish. Okay, this is the real crappy part if you don't remember the other part we talked about, right? How it's like one moving's forward, one's moving away. So, we're dealing with velocity versus time, which means speed versus time, right? So, the object is moving away from the point of origin at a steady speed. Velocity versus time, right? So if it's steady, it's going to be a flat line. If it's on the positive side, it's away. Negative side is towards. So if it's moving away at a steady speed, it's going to look like this. Positive, from here to here moving means away. Toward. Steady speed means it's a flat line. I know that's not exactly straight, but it's the best I can do. Alright, the object is standing still. Okay, well, this is not moving at all over a period of time, so just follow this line. Standing still. Easy. The object moves toward at a steady speed for 10 seconds. So, let's say this is, so toward is opposite of away, right? So we're going to go about here at a steady speed for about 10 seconds. We'll say that's about 10. Then stand still for 10 seconds. So we're just going to be like, boom, right? There we go. So moving toward, because it's on the bottom, and then stand still. Alright, number 4. The object moves away at a steady speed for 10 seconds. Well, that's the opposite. Boom. And then reverses direction and moves back towards. Okay, don't get screwed up by this. Just follow what you know. This is away, this is towards. It moves away, then reverses, and moves towards. Boom, boom. Just follow what you know. Easy money. Alright, let's keep going. Alright, here we go. Now, we are at a velocity versus time. So they're giving you a position versus time on the left. You're going to convert it to velocity versus time. I'm going to do one of these. You guys can do the rest. So, let's do the middle one because it's a little, whatever. I'm doing the easiest one. YOLO. All right, so the position changes pretty evenly over a given amount of time. I'm going to do this 2 ways, and you do whatever way you want. So I'm looking at this, I'm saying it goes 1 meter in 1 second. Then it goes another 1 meter in 1 second, 1 meter in 1 second. So that tells me it's going 1 meter per second. Also, I can know the velocity by distance divided by time. So if I want to be like, yo, the total distance is 4 meters, right? The total time is 4 seconds equals 1. Same thing, right? Same concept, whatever. You're going to have to do 2 different velocities in these because you know they go 2 different velocities, right? So this first one is going positive at 1 meter per second. So I'm just going to do this. Zoop. I'll give you a hint on these next 2. It's going pretty fast for 1 second, and after that 1 second, it's going quite a bit slower. This next one, it's going pretty average fast for 2 seconds, and then it starts going backwards for 2 seconds. Okay, I think that's it. I'll make another video for the lab, and good job, guys. You did it.